Hello, my name is Mackenzie, and today I'm going to be talking about the three problems of antiquity. And this can also be called the three unsolved problems of ancient Greece, and we're going to talk about why that is a little bit later. So starting with just a brief overview, it became the practice in traditional Greek mathematics to accept geometrical constructions only if they could be performed with an unmarked straight edge and a compass. And this custom is derived from the first three postulates of Euclid's Elements. And although none of these postulates refer directly to a straight edge or a compass, this tradition is usually attributed to Plato, and it has become a vital part of Greek geometry. So the Greeks referred to constructing geometric figures using only a straight edge and a compass as the plane method. So from here on out, I'm going to be using the plane method to describe that. And so although the bulk of Greek geometry was constructed using plane methods, there were three problems that defied solutions by the plane method, and those are the three problems of antiquity. So we have squaring the circle, doubling the cube, and trisecting an angle. And all three of those had one thing in common. It was that they all failed. So I have a little picture off to the side that kind of shows the difference between all three of those. There's a little definition under each, but I'm not going to talk about that here. I'm going to talk about that as I go through each one. And then also at the very bottom of that picture, we can see that all three of them were proved impossible in the 19th century, but I'm also going to talk about that later on in the presentation. And we know that none of these three problems can be solved using only a straight edge and a compass, but these failed attempts have helped with important advances made in many areas of mathematics. So I'm going to start with squaring the circle, just a little bit of background. So it means to construct a square whose area is equal to the area of a circle. And so it's very easy for figures bounded by straight lines, such as rectangles and triangles. It was easy to use a straight edge and a compass to do that. So the next step was to square regions bounded by non-linear curves, such as the circle. And although the ancient Babylonians, Indians, and Chinese actually attempted the problem of squaring the circle, it was the work of the Greek mathematicians that made the problem very famous for centuries. So beginning with the Greeks, there were many geometric methods used that allowed the construction of a square whose area was equal to the given circle. However, those methods were not plane methods. So all of the methods used over the centuries that have been found to square a circle, none of them have involved the exclusive use of the straight edge and the compass. So they used, a lot of them used conic sections or more complicated mechanical devices. So when I say that the problem of squaring a circle is unsolved, I mean that it has never been solved using plane methods. So it wasn't actually until the 19th century that the problem of squaring a circle was proven unable to be solved by plane methods. And so now I'm going to kind of just get into some Greek mathematicians who tried squaring the circle. So we have Anaxagoras. He was among one of the first to attempt to solve the problem, but none of his work has survived to modern times. So the first recorded progress was made from the two Greek mathematicians, Antiphon and Bryson. So starting with Antiphon, he started approximating the area of a circle by inscribing a square inside of the circle, then an octagon, then a 16-sided polygon, and so on. And he doubled the number of sides each time. So as you can imagine, as the number of sides of the inscribed polygon doubled, the area of that polygon became closer to the area of the circle. And then Bryson, instead of inscribing a polygon inside the circle, he circumscribed a polygon outside of the circle. So that means to just draw the figure outside of the circle. And so I have a picture of that. So the very top one is more closely related to what Bryson was trying to show. So the square is circumscribed around a circle. And then the bottom one is more related to Antiphon, where the square is inscribed in the circle. And so from both of these, if we had a circle and we had a square inscribed inside and a square circumscribed outside, we could use both of those approximations, and we would know that the correct answer for the area of the circle would have to be in between both of those. And so next, it was discovered by the Greek mathematicians Dinostratus and Nicomedes that the curve called the quadratics could be used to square the circle. And additionally, Archimedes used a curve that he invented called the spiral of Archimedes to square the circle. And both of those methods could not be done using only a straight edge and a compass, though. So it doesn't really follow the traditional method of Greek mathematicians, but it does show that squaring a circle was able to be solved in more advanced methods. Alrighty, and so this isn't like a formal proof. So I couldn't find one online, and I'm sure it's very complicated. So this is just an outline of what Ferdinand von Lindemann was able to find out. So that he proved that pi was a transcendental number, meaning it cannot be the root of an algebraic equation with integer coefficients. So this confirmed that no straight edge and compass construction of a solution to the circle squaring problem was possible. So he proved that it was impossible to square the circle using plane methods. And then just a couple interesting facts that I found. So over time, throughout the centuries, it has become a challenge, kind of like a competition to see if someone can square a circle. And so there was this British mathematician, Augustus de Morgan, who became very obsessed with it, that he actually coined the term morbus cyclometricus, which means circle squaring disease. So I thought that was kind of funny. And then circle squaring work has actually helped aid in the advancements of calculus, specifically integration. So we can thank the Greeks for that one. Alrighty, and so moving on, I am next going to talk about doubling a cube. So we can see, I just have a little definition there. So it means to construct or duplicate a cube with exactly twice the volume of a given cube. So that picture there kind of just shows you how they double the cube. I'm actually going to talk about that picture specifically more in detail within the next couple of slides. And there are actually two stories that come from the Greeks regarding the origin of this problem. So the first is the oracle at Delos. So the oracle at Delos commanded that an altar in the temple, an altar was a cube. He wanted it to be doubled in order to save the Delians from a plague. However, they failed to solve this problem because, as we will learn, it's impossible to solve. And because of this, the plague continued. So that is one of the origins of doubling a cube. And then the other one relates to King Minos. I don't know if I'm saying that right. I'm just going to go with Minos. But he commanded that a tomb be made for his son. And after its completion, he was dissatisfied with how big it was. So he commanded that the cubic tomb be made twice as large by doubling each side of the tomb. And so we know that since the volume of the cube is length times width times height, we wanted to double each of those. So instead of actually doubling the original, it ended up being 8 times the size of the original volume. And so both of these stories may be a myth, may be a fact. We're not actually sure about that. But the problem of doubling a cube using only a straight edge and a compass became very important in Greek geometry. All right, and so I just have 2 examples of a couple people who were able to solve doubling the cube, but they couldn't solve it using plane methods. So these are more advanced methods. We have Archimedes of Tarentum, and he produced a construction of the problem using 3 geometric or dimensional objects, such as a cylinder and a cone. So I included a picture down there, and you can see kind of how complicated it is. Obviously, that all couldn't be done using only a straight edge and a compass. So they had to use more advanced techniques with a cylinder and a cone. And then next we have Menaechmus. I don't know if I'm saying that right, but he found 2 solutions using the intersections of conic sections. And he actually discovered conic sections when he was trying to solve this. So that is one of the great things that we learned from doubling the cube of the ancient Greeks. We actually have conic sections from that. So that's really cool. However, no mathematician was able to succeed in solving the problems using the straight edge and the compass alone. So therefore, we can still say that it's impossible under the plane methods of the Greek geometers. And then we have Hippocrates of Chios, and he found that the problem of doubling a cube could be solved if the related problem of finding two mean proportionals between one line and its double was solved. So that's kind of hard to decipher, so I included an example. So this is kind of how we would say it today. So find two values x and y such that a over x is equal to x over y, which is equal to y over 2a. So from this, we see that we can get the equation x cubed is equal to 2a cubed by cross multiplying, meaning a cube with the side x has twice the volume of a cube with side a. And again, we can see that the Greek geometers were not able to perform this construction using exclusively, just the straight edge and the compass. So I have a little proof included. So in the 19th century, Pierre-Wansel proved that a geometric construction to double a cube using only a straight edge and a compass could not exist. So again, this isn't like a formal proof. This is kind of just what Wansel was able to discover. So we could see in the picture that the smaller cube has a side length of 1. So that would mean the volume is 1 cubed, which is equal to 1. So if we wanted to double that square, we would want the volume of the bigger square to be 2. So in order to find the side length of each side in the cube with a volume of 2, we would have to cube root 2 to get the length of each side, and that is not a constructible number. And so that is how Wansel proved that this is impossible by the method of just using plane method only. However, like as I have said before, using more advanced techniques, they were able to find some solutions to this problem. And moving on to the very last problem of antiquity, that is trisecting an angle. So that's the division of an arbitrary angle into 3 equal angles. And so the construction of regular polygons and the construction of regular solids was a traditional problem in Greek geometry. The Greeks were able to construct any regular polygon with an even number of sides, as well as some with an odd number of sides, such as a triangle and a pentagon, using only plane methods. They could even construct some complicated solids, like regular hexagons, octagons, decagons, and so on. But in order to construct a regular polygon with an arbitrary number of sides, it was required that an arbitrary angle be divided an arbitrary number of times. So for instance, to construct a regular polygon with 9 sides requires that a 60-degree angle be trisected. So the Greeks knew that any angle could be bisected using only a straight edge and a compass, but cutting an angle into 3 equal thirds using only a straight edge and a compass proved to be a challenge. Many mathematicians, such as Hippocrates of Chios, were able to solve the problem, but never by using the plane methods alone. So at the bottom, I kind of just included a picture. The picture on the left just shows a bijection, and then the picture on the right shows what a trijection would look like. So we can see that the angles are split up into 3 even angles. And then, so here are some methods that they were able to use. None of these methods are plane methods. So Greek mathematicians found that they could use conic sections, the quadratics, and the spiral of Archimedes to solve or to triject an angle. So on the left here, this is an example of using conic sections. So we can see that multiple circles are drawn, and from the intersections of those circles, we can create the lines. And so we see there are 3 equal angle lengths right there. So it's split exactly in 3 equal parts. And this is actually an example of a 45-degree angle. And then on the right, we have this pink line right here is the spiral of Archimedes. And from this, we can use that spiral to create 3 equal angles. And we can triject that angle. And then again, another pretty informal proof. In the 19th century, Wansel was able to show that trisecting an angle could be reduced to solving a cubic equation. So none of these curves, however, could be constructed using the restrictions required by traditional Greek geometry. So again, couldn't be proved using the straight edge and the compass. So that was also why it was impossible. And it involved finding a solution to cosine of 3 theta, which is equal to 4 cosine cubed theta minus 3 cosine theta. Again, cannot be solved using straight edge, and a compass. Yeah, I think that is it. So we can see from these 3 problems of antiquity that it has helped lead to a lot of different advancements in math today. Like we saw with doubling a cube, conic sections were discovered. So we have that today, which is pretty cool. And then also with integration, we have that today because of the ancient Greeks and these 3 problems. So even in their failure, we were able to learn from them, and math today wouldn't be the same without it. And there are my sources. So I know that was a lot of information that I kind of just threw at you, but I hope you learned something and found it interesting. Thank you so much for watching.